Before diving into a specific modeling examples, let me also quickly go over a few general remarks about modeling with ordinary differential equations. Okay, here is my first remark. One, when modeling real-world phenomena using ordinary differential equations, using ODEs, we may encounter situations where the quantity of interest takes on only discrete values. For example, population as a function of time. Population is always a whole number, right? That is an example of a quantity that only can have discrete values. Let me write this also. For example, population as a function of time. Since population is always a whole number. In particular, it cannot be an irrational number, right? In reality, let's say that you have a model, the main quantity of interest in that model is the population of a certain species. In reality, that the main variable, the population, is a whole number, right? It cannot be a square root of 2, for example. The population cannot be a square root of 2. In such cases, our differential equation model approximates the inherently discrete nature of the quantity with a continuous function. As a matter of fact, with a differentiable function, with a continuous function. For the sake of simplicity and mathematical tractability, right? Remember, the unknown in your differential equation, the quantity of interest in your differential equation, you have the derivative of the unknown in your differential equation. So every time you are dealing with a differential equation at this level, the unknown function must be a function that is differentiable. In particular, it must be continuous, right? And what we do in these cases is that our model thinks of that discrete quantity as a continuous quantity, as a quantity that is varying continuously. It can attain all values, not just like discrete values. So just to be like very clear about what's going on here, as a continuous function, let me say for the sake of simplicity, we want to create a simple differential equation model for the sake of simplicity. Okay, now this is what I mean. Let's say that you have, and we will discuss these things carefully when we talk about the specific examples. Let's say that you have a model And the main purpose of that model is to predict the population of a certain animal species. What that model will create for you is an equation, is a differential equation, where the main unknown is the population, as a function of time. So we have population, and then time here. And then when you solve the differential equation, the solution to your differential equation will be some differentiable curve, some continuous curve. For example, let's say something like this. This is the solution obtained from ODE model, model. Of course, the real world data, the population cannot attain any value. The real world data will be something like this. For example, at the time, let's say that in years, the time here is in years. And then in year 1, for example, the population has this value, some integer value. In year 2, another value, integer whole number value, 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 and so on and so forth. Of course, your model is not giving you exactly those whole number values, right? There's those integer values. This is some continuous approximation of what is happening in reality. So the moral of the story here is that you should not be surprised if your model produces non-integer values for a quantity such as total population. So when you develop your differential equation model, you are making this approximation. You are approximating that quantity that in reality only can attain discrete values with a quantity that varies continuously. As a matter of fact, unknown to a differential equation, the unknown function to a differential equation at our level is always a differentiable function, because the derivative of the unknown appears in the differential equation. Not only it is a continuous curve, the solution is a differentiable curve, to say the least. So keep this in mind. Don't get surprised if you have like a quantity, you're modeling that quantity. In reality, that quantity can only attain integer values, whole number values. But when you construct your differential equation model, solve the model, you will arrive at maybe irrational values for that quantity. Remember that this is like an approximation of that actual value that happens in reality. So let me actually write this also, just to be very, very clear. So we should not be surprised if our model produces non-integer values for a quantity such as total population, All right. Very good. Now I want to make a second remark about the ODE models. One last comment that I want to make about this situation is that also it is the case that sometimes the unknown function in these scenarios, it's not actually the total amount of population. Maybe it's the percentage, right? In those cases, even you may have even rational numbers as percentage, and they represent a total integer number for the total population, right? For example, you can talk about like 2.5 million, right? 2.5 million. 2.5 is not a integer, but 2.5 million is a perfectly legitimate number for the total population in the real world, right? So depending on what exactly the function represents, it may be the case that even in these cases, non-integer values may make sense in reality. But that aside, it is also the case that we are approximating a discrete collection of values with a continuous curve. I think that's the more fundamental reason as to why you should expect to see non-integer values in such models. But now I want to make a second remark here. So two. So my first remark was that sometimes we are approximating a quantity that is in reality discrete with a continuous curve. The second remark is as follows. When constructing a differential equation model, an ODE model, here our focus is on ordinary differential equations, of course, we are often interested in the change in the quantity of interest over a time interval delta t, over a time interval delta t. Why is that? Why are we? Let's say that our quantity of interest is S. Let's give a name to the quantity of interest. It's a quantity, is a function of time. S as a function of time is the quantity of interest. And then why should be interested in the change in S over an interval delta t? The reason goes back to the definition of derivative. Remember, when we want to construct the ODE model, our job is to find a differential equation that S must satisfy, right? And remember that the derivative ds dt is the limit of s of t plus delta t minus s of t divided by delta t. So if I want to construct an equation that involves the derivative of t, I should be interested in seeing what will happen to s as I move from time t to the time t plus delta t. Let me actually write what I just said. The reason is as follows. In order to come up with an equation that involves the derivative of the quantity of interest. Let's say that our quantity of interest is S, ds dt, an equation that was ds dt. We know that ds dt, by definition, is the limit as delta t goes to 0, s of t plus delta t minus s of t divided by delta t. So we need to explore s of t plus delta t minus s of t. That is why we're interested in this difference, in what is happening to s over the time interval delta from t to t plus delta t. We can start with investigating. We need to investigate. We can start with investigating s of t plus delta t minus s of t. So this actually happens a lot in many of our models when we want to come up with a differential equation for the quantity of interest s. We start by understanding this quantity, s of t plus delta t minus s of t. And of course, ultimately, we keep in mind that we want this delta t to be very small. We want to take the limit as delta t goes to 0. We want to divide this by delta t and take the limit as delta t goes to 0 to come up with the derivative. But this is a quantity that usually gives us good information in order to construct a model that involves the derivative of s. Remember, the job here is to construct a model that involves the derivative of s, the derivative of the unknown quantity, the quantity of interest. That is an ODE model, right? Okay, now keep that in mind. In reality, Such changes, the change in the value of S from T to T plus delta T, such changes may not occur, may not happen continuously in time. Let me explain this further. Continuously in time. So what do I mean by this? For example, so again, let me repeat. When I say such changes, I mean the change in the value of S from T to T plus delta T. What the value of S is at time T and what the value of the unknown quantity is at time T, what the quantity of interest is at time T plus delta T. This change, my claim is that in real life, it's not necessarily happening continuously in time. And let me explore this by giving you an example. For example, consider a scenario where a bank adds $1 to your deposit per day. So in reality, obviously, there is a specific time during the day where the bank adds that $1, right? In reality, there is like one specific time during the day where your deposit will change. The amount that you have deposited in the bank changes. So in reality, the addition of $1, the addition does not happen continuously during the day, throughout the day. Does not happen continuously throughout the day. Right? Instead, at a specific time each day, at a specific time each day, the bank adds $1 to your account. The bank adds $1 to your account. So here the quantity of interest is the amount of money that you have in your account. And then in reality, what is happening is that there is a specific time during the day where the bank adds the $1. Now, but let me tell you what we will do when we want to create an ODE model, where the unknown is the amount of money that you have in the bank. However, in our models, we typically assume that this change, this addition of $1, that this change occurs continuously over time. So what does this mean? This means that during any interval, of delta t, no matter how small delta t is, the bank, we make the assumption that the bank adds 1 times delta t dollars to your account. For instance, just to be very, very clear about what's happening here, for instance, over the course of 1 hour, over the course of 1 hour, the bank would add, this is our assumption. Of course, the reality is different. The bank would add $1/24, right? Because delta t here is 1/24. One unit of time here is 1 day in this model that I'm explaining. 1 hour will be 1/24. 1/4, $20. And of course, over 24 hours and over 24 hours, which is 1 day, 1 unit of time, which is the 1 unit of time in this model, 1 unit of time, this is when delta t is 1, this is when delta t is 1, the total would sum to $1, which agrees with reality. The total would sum to $1. So they ultimately disagrees with reality. In 1 day, you will have $1 more in your account. However, the way we are assuming that this is happening, this increase in the amount of money is happening, is continuously through the time. It's not just one specific time, right? Okay, this is the assumption that we will be making in many of our models, and you will see this in action in some of the models that specific models that we will discuss. So this continuous change assumption obviously simplifies the modeling process, and as you will see, it will help us in constructing our ODE models easily. All right, so let me also just I'll give you another way of thinking about what I'm talking about here. So hopefully this example clarified simplifying the simplifying assumption that we will be making in some of our models, the fact that the change is happening continuously in time, no matter how small delta t is, there is still an increase in the amount of money in your bank account. Even if delta t is 1 minute, there is still an increase in the amount of money in your bank account. This is the assumption, the simplifying assumption that we'll be making in some of our models. Let me give you another way to think about what's happening here. Another way of thinking about this idea that we just discussed. In other words, when constructing some of our ODE models, we make the assumption that we assume that the instantaneous rate of change, which is the derivative, the instantaneous rate of change, which is the derivative. This is when you take the limit as delta t goes to 0, is the same as the change per unit of time. And unit of time depends on the application. In the example that I just told you, unit of time was 1 day, but unit of time maybe 1 second, maybe 1 minute, depending on the application. So as a matter of fact, this phrase that we have on the right, it can be a little bit ambiguous in a sense. And in general, if you want to be precise and rigorous, this equality does not hold, right? There is a difference between taking the limit as delta t goes to 0 and then talking about change in 1 day. These are not exactly the same, but we make this simplifying assumption. Just in terms of mathematics, is that so this left-hand side, is ds dt, which is limit as delta t goes to 0 of s of t plus delta t minus s of t divided by delta t. And then this right-hand side is s of t plus 1 unit of time, change in 1 unit of time, minus s of t. You can also divide this by 1, right? It is the same. Dividing it by 1 or not dividing it by 1 is the same. And we are identifying the left-hand side with the right-hand side. We identify the left-hand side with the, they are identified. So this left-hand side is identified with, considered the same as. Identified with means considered the same as. In some of our models, we do this. Now, how accurate this is, then later we can look at the results of our model and compare it with real-world data to see whether was a good approximation or not. So just another way of writing this exact same thing is that what I'm doing here, in a sense, is that I'm thinking of s of t plus delta t, s of t plus delta t minus s of t, and I'm approximating this with delta t times s of t plus 1 minus s of t. This is change in per unit of time, in 1 unit of time, change in 1 unit of time, and I'm making the assumption that if I multiply that by delta t, that will give me the change in delta t units of time. Change in delta t units of time. I'm making the assumption that at least for delta t very small, this is true. That is because ultimately I will take the limit as delta t goes to 0. I'm making the assumption that for delta t very small, for small values of delta t, this approximation is a good approximation. This will happen in many of our models and of our ODE models, that for delta t very small, this approximation will be a good approximation. For delta t small, because ultimately what I care about is the limit as delta t goes to 0. So I can divide both sides of this last equality by delta t, and then take the limit as delta t goes to 0 to get the identification that I showed you above. This is the assumption that we are making in some of our ODE models, that at least for small values of delta t, this approximation is a good approximation. All right, very, very good. I have one last remark, one final remark about the constructing these ODE models, and I hope that you're enjoying these remarks that we are going over. Normally, it is the case that many of the resources that we have out there, they implicitly take advantage of these observations, of these remarks in their solutions, but they do not explicitly mention these assumptions that are being made, these approximations that are being made. So we are trying to be very careful and trying to be like honest about what we are doing in our modeling process. So I have one final remark, which is again very interesting. So 3, this will be my third remark. And this remark should feel familiar, as the reasoning mirrors the logic you encountered in your calculus courses when developing formulas for computing areas and volumes. So hopefully what I will discuss in this remark will not look completely alien to you. It should remind you of certain procedures that you were introduced to in your calculus courses. So let's see what is my third remark is. My final remark is about construction of ODE models. Suppose f is a continuous function. If delta A is very small, is a very small quantity, is very small, in the sense that eventually we have the intention of taking the limit as delta A goes to 0. This is how you should interpret what I'm talking about here. Eventually, the intention is to, the intention is to let delta A go to 0. We can approximate, so assuming that this delta A is going to be very small, we can approximate the function f over the interval from A to A plus delta A by a constant function, whose value for any input in the interval from A to A plus delta A is always f of A, is equal to f of A, is always f evaluated at A. So let me draw a picture that may help in better understanding what is happening here. So let's say that I have an interval from A to A plus delta A. This is my interval. And then I have a continuous function that is defined on this interval, like this. This is my function f. It is the graph of the function f. So just to be very, very clear, so this will be f evaluated at A. This will be f evaluated at A plus delta A. So f is not necessarily a constant function on this interval. What I'm telling you here is that if this interval is small, if you ultimately, you know that ultimately you're going to take the limit as delta A goes to 0, you can approximate. So let me do approximation. The function f with a constant function over this interval. So again, assuming that the interval is very small. So here we go. Instead of considering this f that you see on the left, I'm going to just consider f of A, and this will be my approximation of the function. At all points, its value is f of A, right? Now, this is a good approximation for the function f as long as delta A is small. Obviously, this approximation becomes more and more accurate as delta A goes to 0. Clearly. Again, remember like the way you define integral, for example, in calculus 2 or calculus 1, and then you had these partitions, and you said ultimately what you did is that you made sure that the length of each interval in your partition is going to 0 to make your approximation better and better. Clearly, this is the approximation of f. Approximation of f by a constant function. Clearly, this approximation becomes more accurate, becomes better and better, becomes more accurate as delta A gets smaller and smaller and smaller. Awesome. Now, let me show you some examples of this. The idea I think I explained, but I'm going to show you some, like maybe in a sense, more concrete examples of this that will be very helpful in understanding the constructions of some of our ODE models. So here are some examples. Here are some examples. Examples. So example one, let's say, for example, that the profile of the velocity of a particle that is moving on a line is given to you. A particle, it has a one-dimensional motion. It is moving on a line. And the velocity of the particle is given to you. So let's say that this is velocity. Since the motion is one-dimensional, we can represent velocity by a signed quantity, by a signed number. We don't need to worry about vectors. So, and then here, this is time. And then you have t, and then t plus delta t. And you have a profile for the velocity. This profile is given to you. Let's say that the profile of the velocity looks like this. And here we go. This is the profile of your velocity, right? So this is v at t. That will be v at t plus delta t. And someone asks you to find the displacement during this time from t to t plus delta t. So assuming that delta t is small, let's for a moment assume that ultimately I wanna think about the delta t as it goes to 0. Assuming that delta t is very small, I'm gonna change the color here. Approximation, assuming delta t is small. Is approximation, assuming delta t is small, assuming delta t is small, right? As we discussed, for delta t is small, we can approximate this profile with a constant profile. So here we go, we have t, and then t plus delta t. And then I approximate my velocity. I will use the letter v for the velocity. With this constant velocity, the profile initially was not constant, but since delta t is very small, I can do this approximation. This is just v at t. At any point, I will look at what the value of v at t was, and then I'm going to assume that at all points in the interval from t to t plus delta t, the velocity is equal to v at the left end point, which was v at t. So this is our approximate velocity profile. Approximate velocity profile. Now you can think of this particle moving with constant speed during the interval from t to t plus delta t. And then this immediately tells me that, so if I use this approximation, that tells me that the position t plus delta t minus x of t, the displacement is approximately v of t delta t, the area under the graph of v, right? So in a sense, I approximated the area under the initial velocity profile with the area of this simple rectangle, v of t delta t. And of course, you immediately can say, yes, this approximation becomes better and better as delta t goes to 0. Because this tells me that x of t plus delta t minus x of t divided by delta t is approximately v of t. And yes, as delta t goes to 0, this is exact. That is the definition of v of t, the derivative of the position with respect to time as delta t goes to 0. So again, this approximation becomes more accurate, accurate as delta t goes to 0. So I want you to get used to this idea that if you have a very small interval, a continuous function over that interval, you can approximate the function on that interval with a constant function, and the value of that output is the value of the original function at the left endpoint. That is a process that I want you to get very comfortable with. I'm not saying that this is the only way you can approximate your function, but this is certainly one way that you can approximate your function, and it becomes more accurate as delta t goes to 0, as the length of the interval goes to 0. So let me show you another example for those of you who are interested in mechanical engineering, structural engineering. A big part of it is the study of deflection of beams under arbitrary the loadings. So let's say that this time I have a beam and I'm interested in the portion of the beam that occupies the interval from x to x plus delta x. So there is an elastic beam here. Okay, here. This is x plus delta x. And then the vertical axis here is the loading density. Loading density, right? The force per unit length that is applied to this beam. So this is I'm gonna draw the actual profile of my loading density. So let's say that it's gonna look like this. So whatever. So these are the loads that are applied to this beam. Okay, I'm going to denote load by the letter P, the density of the load by the linear density of the load by the letter P. So here we have P evaluated at X. Here we have P evaluated at X plus delta X. And then you're interested in the total load that is applied to this segment. Let's say that is a quantity of interest. So this is the actual profile of the load, the density of the linear density of the load. And now you want to find the total load, total force applied to this segment of the beam. So, and again, I'm going to use the technique that we just discussed, approximation, assuming delta x is small, assuming delta x is small. And maybe with the assumption that ultimately I want to let delta x go to 0. And then what I will get here is that I have this segment of my elastic beam here from x to x plus delta x. I'm going to approximate, assuming that delta x is small, I'm going to approximate this load with a uniform load, a constant load. The value is P at X. I'm going to look at the value of the actual profile at the left endpoint, and I'm going to assume that all the way from X to X plus delta X, the value is equal to that value that I had at the left endpoint. And now I can easily compute the total load. So the approximate to the total load on the segment of the beam, from x to x plus delta x is approximately P of x delta x, right? The area under this load density on the right-hand side. And this approximation obviously again becomes more accurate as delta x goes to 0. And then one last example of this idea that when you're dealing with segments whose width are getting smaller and smaller, you can do these approximations. So suppose that we are interested in computing area of a segment of some object. Let me draw a picture here. Let's say that we have a segment like this. This is the y-axis. This is the x-axis. I'm interested in the area of this segment. I'm interested in the area of this segment. And then let's say that this is the y coordinate, and this is y plus delta y. And again, assuming that delta y is small. Assuming that delta y is small. Let's say that the length of the bottom side, the sides are varying with the y, with the height. The length here, let's say that it's a function of the height. This is the length here is f of y. The length here is f of y plus delta y. So this is the length of the top the side, and the f of y is the length of the bottom side. So this like width that we have, it changes with the height, and that function, the function that represents the width, I'm denoting it by f. Now let's say that you want to understand this area again. So this is shaded. This shaded region is the area of interest. We can use our techniques, and these are things that you should be familiar with from your calculus courses. Assuming approximation, assuming delta y is small, approximation, assuming delta y is small, maybe ultimately you want to let delta y go to 0, assuming delta y is small, right? What we will do is that we will assume that this function f is a constant function. I'm not going to consider the change in the value of f in this small interval. That means that I'm approximating that area with this area. So this is y. This height is y plus delta y. The length of the bottom still is f of y, but the length of the top is also f of y, right? Like exactly, I'm assuming this f is a constant function over the interval from y to y plus delta y. And then now I can approximate I know the area of a rectangle. So the area of interest, this area of the shaded region, on the left is approximately f of y times delta y. This is the width times height. The height on the right is delta y, the width is f of y. And of course, this approximation, as usual, this approximation becomes more accurate, as delta y gets smaller and smaller, and smaller. All right, I'm done with my observations, with my remarks. So what we did in this video is that I went over three observations, three general remarks that can be helpful in later understanding some of the things that we do in the process of constructing our ODE models. Most of the resources that we have out there, they implicitly use these ideas, but they never explicitly mention them. What we did in this video is that we were very clear and honest about certain processes that we use in order to construct our ODE models. One, sometimes we are dealing with values that in reality, with quantities of interest that in reality, they only attain discrete values, but in our ODE models, we approximate those quantities with quantities that vary continuously. That was item number one. Item number two, do you remember what the second item that we discussed was? The second item that we discussed was the following: the fact that the changes that we are considering in reality, sometimes they are not happening continuously in time. right? There is a specific time where certain changes happen, but in many of our ODE models, the assumption is that the changing are happening continuously in time. And as a matter of fact, in many times, the way we think about the change in our function, at least for delta t small, is that the change during from the interval from t to t plus delta t, between t and t plus delta t, is delta t times the change in 1 unit when the t goes from t to t plus 1, as you see in the formula that we have here. And finally, this idea that when we are dealing with small intervals, we may be able, especially if ultimately we want to take the limit as the length of the interval goes to 0 in the process of constructing of our model, we may make the assumption that our function f is constant, our continuous function f is constant over the interval. You will see all these ideas in action in the specific modeling examples that we will study in future videos.